Well, what I want to do is take a moment and walk you through a problem, which is asking us to graph a function. Now, in order to graph this, we got to figure out the critical values, the maximum and the minimums, as well as the inflection points. In this given problem, the function has been provided in the expanded form and also in the factored form. Now, the expanded form, it is useful, but the factored form is so much more powerful than the expanded form. Don't get caught in the trap that you're going to have to use this expanded form. It'd be a whole lot easier if you use the factored form. Let me go ahead and show you. The first thing is I might want to go ahead and just identify the intercept points. We have to do that eventually in the second part anyway. I could set my function equal to 0, but then it's going to require me to factor this. Luckily, it has already been factored, so I don't have to worry about that much in this particular part. I see that the intercepts are going to be at 0 and also over here at 4. Now, in order to find the critical values, I'm going to have to take the derivative and see when this equals 0. And because it is a polynomial, I don't have to worry about the case when it's going to be undefined, because the derivative for a polynomial, that's always defined. Now, guys, I could do this. I could come over here. I could take that derivative. I can apply the power rule. But what is this going to require me to do? That's right. I'm going to have to factor this. Can you factor this? Not easily, and definitely not really fast. So instead of taking the derivative of the expanded form, it might be to your advantage if we take the derivative of the factored form. And because it has a power on top, that makes it really, really easy to factor. Let me show you. Again, I do have a product, so I'm going to have to apply the product rule in order to take the derivative. Derivative for the first function is 1. I'll leave the second function alone. And the derivative for the second function, well, that's going to correspond to 3, x minus 4 to the second power, and I'll leave the first function alone. And guys, look at this. I got a common factor. I can factor that piece out. X minus 4 squared, then I'll have x minus 4 plus giving us x minus 4, 4x minus 4, and I'll factor that out as well. So our first derivative, we found that very quickly by not falling into the trap of using the expanded form, but using the factored form. And if you can keep something in factored form, by all means do. Factored form has a lot of power to it. And remember the tenet. Keep things in factored form for as long as you possibly can. It usually makes problems a lot easier to navigate through. Here we'll just pull out the 4, and we'll be left with x minus 4 squared minus 1. So our critical values, we're going to have 1 and 4. So we can go ahead and record that. And in order to figure out what's happening here in terms of increasing and decreasing and max and mins, I just want to see what's going to be happening with my derivative. If my derivative, if it's decreasing, if my function is decreasing, then my derivative is going to be negative. If my function is increasing, then my derivative is going to be positive. And look right here. Do you see how that's being squared? That's not going to contribute to the polarity of my derivative. This value is always going to be positive if I pick a test point, something like 0, 2, or 5. What's really driving it is this piece back here. And if I plug in the 0, I see that this component, that's negative, And that component, it's -4. You square it, you get 16. But again, we're not concerned about the numerical value, just the polarity of the number. So we see that it is going to be decreasing. And then plug in the 2. We're going to get positive here again. We're going to get positive here. And then if I plugged in the 5, this is also going to be positive. So immediately we see that the graph, it is decreasing from -infinity up to 1 and increasing from 1 to 4 and 4 to positive infinity. And I also see an inflection point. I see that echo of that inflection point that we're going to see in a moment. Let's go and write it down. We'll come back to here in a moment. But also note that the graph's going down, then it's going up. Guys, that's a minimum value. So we have a minimum located at x equals 1. Now, the actual minimum value is not x equals 1, but rather is the function evaluated at 1. Now, you have an option. You can use the expanded form again, but that's more complicated than using the factored form. If I just plugged in a 1, we're going to see very, very quickly 1 times -3, that's been cubed. So what we get here is -27. That's the minimum value. Just remember, minimum and maximum values are y values. They're not the x values. All right. And do you ever see a spot in the graph where it goes up, then goes back down? I don't either. So what's that tell us? That's right. There's no maximum. Look what we got just by looking at the first derivative. A wealth of information. And I already know what my graph's going to look like. It's going to go down, it's going to go back up, and back up again. Okay, so we'll keep that in the back of our minds. We have an idea the graphs can go down, then up, and then up. Okay, now to figure out the concavity, we're going to have to look at the second derivative. Now, to find the second derivative, I can do the same thing. I can come over here and I could think about if I want to use the expanded form. Not really. I see it's going to be a little more complicated than just using the factored form. So let's go and use the factored form, and let's go ahead and pull that 4 out so you can see it a little bit easier. So for the second derivative, it is a product, so we're going to be applying the product rule. 2 times 4. Then, derivative for x minus 1 is 1. And I want you to pay attention again. Do you see how in these two terms we have a common term? Do you see how there's an x minus 4 and x minus 4 that we can factor out very quickly? That's because it was raised to a power. So although I do have this thing being raised to a power, that's going to be very helpful to us when we start factoring. So don't shy away from it. Jump on it. It's a gift. So factor it out. X minus 4. And we can pull out the 4 as well. We're going to have 2, x minus 1, x minus 4. Get a little bit of cleanup. We'll have a 2x, but I have an x back here. So I have a 3x. Then a minus 2, but I do have a minus 4, minus 6. So we can pull out a 3, so we'll have 12. X minus 4, x minus 2. So our inflection points for our function f is whenever the second derivative is equal to 0 or where it's undefined. Again, since it is a polynomial, I don't have to worry about being undefined. It's going to be defined everywhere. And I see the second derivative is 0 at 4. Remember how we found it earlier when we looked at the first derivative? And also at 2. Okay, now the next thing is I just want to take a moment and analyze what's happening with the polarity of the numbers. So if I was going to plug in 0 or plug in 3, what's going to occur? And a good test point is 0, if you can choose it. Let's try 3 and let's try 10. Okay, so when you plug in 0, again, you're not concerned about the number. You're only concerned about the polarity. Is it positive or negative? Get negative. Plug it in. 0 minus 2, but again, I'm just concerned that's negative. And when you plug in 3, you get minus 1, and then positive 1. You're going to get 6, but again, I'm just concerned that it's positive. And then down here, get 8, positive. So negative and negative gets me positive. Then I'll have negative, then I'll have positive. Now, remember the emojis we talked about. This is going to help out. Whenever the second derivative is positive, oh, happy days, you're concaved up. And whenever the second derivative is negative, down like a frown. So I know that this function is going to be concaved up from negative infinity to 2. And also, all the way from here, from 4 to positive infinity. So concaved up, concaved up. And right there in between, from 2 to 4, is concave down. So from 2 to 4. Now, the actual inflection points, to find those, what I'm going to do is take 2 and 4. I'm going to plug into the function. And 4 again, that was an intercept. Makes that really easy to find. And to figure out what happens when f equals 2, I am not going to use the expanded form. It's way too complicated, way too hard, takes way too much time. Plug it into the factored form. So much easier. Two minus 4 minus 2 raises to the third power, minus 8. So the inflection point at 2, the y value is going to be minus 16. And at 4, the y value is 0. All right, so let's put all the pieces now to the graph together. So we have a minimum value at 1, which reaches all the way down to minus 27. Then over here at 2, at about minus 16, we're going to have a point of inflection. That's where the concavity is going to change. And as this graph's coming down from negative infinity to 1, it's decreasing. So I want my graph to come down this way, hit that minimum value. And notice how we are concaved up. It's that part. And I want to make it all the way up to the other side. It still needs to be concaved up until I get to 2. And when I get to 2, the concavity changes. So from 2 to 4, I'm going to pick a bend in it. I don't want to keep going like this, nor do I want to do this, because that's concaved up. I want it to be concave down. So I'm going to change it so it's more concave down. Then I am going to be concaved up again from forward to positive infinity. So on the other side, I'm back to being concaved up. Okay, so take a moment, review this problem, see if it all makes sense to you. Review how we found the first derivative, how we didn't use the expanded form, but rather we used the factored form. Because the factor form is a whole lot easier. It allows us to factor the polynomial when we're looking at the first and second derivatives. And it allows us to also do the evaluation a lot easier than using the expanded form. Okay, so take a moment, review this problem, see if it all makes sense to you. And if you need any help, just let me know. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.